We talked about our tangential acceleration, which is an acceleration of speeding up or slowing down. And this was measured in meters per second squared. But there's also the acceleration we talked at the very beginning of the year, the acceleration of changing direction. So even if we are not speeding up or slowing down, the fact of moving in a circle, we are accelerating. And we refer to this as a centripetal acceleration. So we use the subscript C for centripetal acceleration. Think of it this way. Let's say that you're in the car, and perhaps you graduated, you have your tassel hanging in the rear view mirror. And so what happens is, as you're driving, let's say you accelerate forward. What's going to happen if we accelerate forward is that our tassel is going to move backwards. Now the reason it actually moves backwards is because of inertia. You move forward, the tassel stays still. But the idea is that the tassel moves in the opposite direction of the acceleration. Well, what happens if now we're moving really fast and we slow down, so we accelerate backwards? Well, the tassel now moves forward. And again, the idea is that inertia, the tassel keeps moving even though the car stops. And looking at it visually, the tassel moves in the opposite direction of the acceleration. So what happens when we move in a circle? Well, from an overhead view here, here's a circle we're moving in. From an overhead view, looks like the tassel is going to move to the outside. And we just said that the tassel always moves in the opposite direction. We accelerate. When we accelerated forward, the tassel moves back. When we accelerated backwards, the tassel moves forward. So if the tassel moves to the outside, the acceleration must therefore be towards the inside. And this is what we refer to as the centripetal acceleration. So how do we use the idea of inertia to explain why the tassel is actually moving towards the outside? What's happening is the first law of motion says all objects want to continue moving in a straight line. Not just continue moving, but continue moving in a straight line. So as the car turns, the tassel wants to keep moving forward, but the car pulls it inward. And that's why it looks like the tassel is actually moving towards the outside. It's simply inertia. The tassel moves forward, the car is the one that turns. And so our centripetal acceleration is the acceleration of any object that's moving in a circle, and it's directed towards the center of the path. That's where we get the name centripetal. Centripetal is Latin for center, seeking, to seek the center. So hopefully the idea of the tassel as you're driving in your car will help, but also the word itself, centripetal, means towards the center, has center in its name. So even if we're moving at a constant speed, even if the speed of that car is a constant, let's say 10 miles per hour, you are changing direction, and therefore your velocity is changing, and velocity change equates to an acceleration. Symbol is the letter A, which means that it is a meter per second squared. And then our equations are Vt squared, the tangential speed squared over the radius. And we can easily derive the second equation if we say, here's our equation for centripetal acceleration. However, we had talked that the tangential velocity is the radius times the angular velocity. That's how we get back and forth between angular and linear. We multiply or divide by the radius. So if I now replace my tangential velocity with r times omega, I've got to square it. When I square that, I have to square both the radius and the angular velocity. One of the radii cancels out, and we're left with r times omega squared. Now notice that when I use this equation, I must be in radians. So now, since I've used that equation, I must be in radians for my derived equation as well. To recap here, all these types of accelerations we see here, we're actually just all of our values. We have our linear versus our angular. We have our arc length, also known as our x, and that's measured in meters. And our theta, which is our angular displacement, is measured in radians. And then we had linear velocity and angular velocity, radians per second versus meters per second. And then our acceleration, we had angular acceleration of radians per second squared. And here we have two of them. Our tangential acceleration, which is speeding up or slowing down. And our centripetal acceleration, which is from changing direction. Both of which are in meters per second squared. So English letters in the linear column, all meters in the linear column. Greek letters in the angular column, all radians in the angular column.